So hello, everyone. Had a good afternoon in London. It's still morning in Boston. I'm going to talk about artificial intelligence in medicinal chemistry, opportunities and challenges. So, I see many audience are coming from different disciplines for this conference. So I just want to say what medicinal chemistry is. Medicinal chemistry is about designing and developing small molecule drugs. In the previous talk by Professor Liao, you have heard about several medicines, drugs to treat the SARS-CoV-2 virus. These are all older antiviral drugs. Most of them he listed are small molecule drugs, except for one interferon, which is a biologic drug. So we, in medicinal chemistry, we design novel drugs for novel diseases. And when I say artificial intelligence, when it comes to drug discovery, we are mostly doing machine learning and deep learning. So this is a very new, technology and impacting a lot of areas in our life. And it is also getting adapted into a drug discovery process. So the idea is that that if you see the picture on the right, it is the let me get my screen title. I thought I will get I don't worry. Okay. There is image, right? The promise of deep learning is that you can distinguish a bird from a cat. So the idea of applying the same technology in drug discovery is that you can distinguish a drug from a non-drug. There are a lot of chemicals you can make, but only few become drugs in small molecule space, right? So can you distinguish a molecule as a drug or a non-drug? That is the promise here. So we do several things in the process of discovering drugs. We do a lot of computational work, and this is more on the computational design, so-called virtual screening, hit and lead generation and lead optimization, synthesizability assessment, binding energy predictions, ADME and properties predictions, and DIL data analysis. These are the several areas of research we utilize medicinal chemistry. We utilize AI methods, particularly ML and DL. And for this talk, because of shortage of time, I will focus on two things. One is emerging, that heat and lead generation, novel way of lead generation using machine learning and deep learning. And also associated with this, that all those molecules which are generated by machines can be synthesized in the lab or not. That assessment also can be done using ML methods. And also, not only you want find molecules which bind to target tightly, but also the molecules which have the right properties so that they get into the right place. Once you take it orally, it survives your gut and it gets absorbed into bloodstream and it reaches the place of action. So that is why we optimize on so-called ADME and properties. So prediction is important. So these are the 2-3 areas I will cover in this talk. So I want to first of all, take you into 1987. It's that 1980s or the time when the so-called structure-based drug design became the new technology for discovering drugs. Otherwise, it used to be very trial and error approach. More rational approach came to being using structure-based methods in 1980s. That is facilitated by availability of crystal structures of protein targets. Crystallography made several advances. Protein engineering made advances so that you can produce proteins of interest and determine crystal structures. The other thing which happened around that time is availability of supercomputers. This picture I'm showing you is the 30-year celebration of San Diego Supercomputer Center, which was, in 2007. And they chronicle what happened over those 30 years from 1987 to 2007. And this text I'm showing you is describing a pioneering effort of predicting binding energy, between a small molecule and a protein. That's by Professor Peter Coleman's group, and that as they said, is revolutionary because now you can not only make predict the binding in silico, in the computer. You don't have to do the measurement. So that is a big advance, and so that so-called structure-based drug design approach was very impactful. I'm showing you two examples here. One is HIV protease on the left and hepatitis C protease on the right. These two projects I was involved at Vertex, in early 1990s. Both have been successful using the structure-based design methods, which uses computational, techniques at that time. And both, produced successful drugs which are, approved and marketed. One is the Emprenavir. It took about 8 years, and that's by that time very, very fast timeline. And we had to make only 340 compounds to get the drug molecule. On the other hand, this the right side is a hepatitis C protease, which is it took longer, but even then, it's only 1,000 molecules. We made about 1,000 molecules, and we discovered a drug called tenofovir. Both are successful. So the promise of structure-based drug design delivered. These are the two projects I'm involved at Vertex I'm talking about, but there are several more successes. The other promise of 1980s is that you can use in silico methods entirely to design drugs. So you get the structure of a protein, there is a cavity, and you want to fill that cavity with the right type of molecule, and you block the function of that protein, and you get the drug, right? That's what I showed in the previous structures. So there you're doing various methods to do that, experimental methods combined with computational methods. The promise was that you can do only entirely computational methods. You can design molecule and also predict binding, and you can take it to a higher level of testing. That's by speeding up drug discovery. That promise was not delivered, in those 2 decades after this, this structure-based drug design method came into picture. But there were lots of efforts to do that, both in academia and industry. There were, this review in Nature Drug Discovery, Nature Reviews Drug Discovery in 2005 describes about 30 methods of this de novo drug design. And GenStar and Breed are the 2 methods we published at Vertex at that time. But it was not that successful. One more pragmatic one is the Breed, where we took crystal structures bound to, 2 molecules bound to the same protein, 2 crystal structures, and you overlay them and hybridize. So if you look at the red bond, right, you can cut that red bond, and you can swap these 2 pieces. So that way you can generate 2 molecules. This was more successful. This actually, this particular method was also put into commercial software, and it was more successful. But the question, the problem remained that can you make those? We can still generate a lot of unrealistic molecules during using these molecules. And the chemistry doesn't make sense. It may not be synthesizable. Here, the molecules are more or less guaranteed to bind tightly to the target because it has all the features of these tight binding molecules. But it may also run into the problem of synthesizability. Can those molecules be made in the lab? That assessment was not available at that time. But the big moment came a couple of years ago. I'm describing two events, 2 publications here. One was in November of last year. I call them AI's AlphaGo moments in drug design. This is a 50-year-old challenge in biology. The premise is that if you know the amino acid sequence of a protein, you should be able to predict the 3D fold, how they actually form a 3D structure. That should be possible. And so that has been a challenge. A lot of very, very smart scientists and structural biologists, computational biologists, been working on this for a long time. And early on, when this competition started, was called CASP competition, only 30 to 40% success was, accuracy was possible. But I will say a bunch of technologies at DeepMind, which is part of Google now, have improved that in 2018 accuracy to almost 60%. And last year, they have actually increased it to 95%, 90+%, and that is almost experimental accuracy. So you get a if you identify there is a protein you want to target, you want to make that protein, stabilize this protein, grow the crystals, do the X-ray crystallography. At the best case scenario, it takes 1 year to get the structure. Now you can get in few hours. So that's huge development to speed up drug discovery. A year earlier, there was another publication. This, a lot of people have been doing, but these people, published this, and got a lot of attention of people in the pharma industry, that they have used AI to design and validate a novel drug candidate in just 46 days. And this is a little bit of hyperbole, hype is there, but there is also some truth to this. There was a lot of criticism of this claim, but it's also a success which we cannot ignore. The criticism is that, say, they took these two molecules and several such molecules and trained the AI, deep learning method, and they generated this molecule. If you look at the novel molecule, there are a lot of features which are, is seen in here, right? In particular, what the novelty is, there's this central ring. That is what they designed. And the criticism is that if you give these two molecules, a trained medicinal chemist can do this on his own by, without help of the machine. And that is true. That can be done by a trained smart medicinal chemist. But what is still important to recognize is that a machine can do this. That's very, huge. So that is the success I'm saying is a big thing. And there are several examples now, and you will get more and more examples as we go, application of medicinal, AI methods to design novel molecules. So I'll go into this we published recently as a book chapter. You can, I have not put the reference, but anybody who's interested can Google, or I can send that information about book chapter. But the deep generative methods, right? Like people have started using deep generative models to generate, new faces of people who don't exist, right? You train the deep learning method to train on some human faces and generate a face which looks like, real face, but it's no person exists like that, right? Same way people are using deep methods to generate music, fake music, fake text articles. So it's very successful in generating, learning from the body of knowledge and generating something novel. So the same thing is applied here. You can train using known chemicals or known drug molecules and train them, you use an encoder and you train that model and you can decode to generate a novel molecule. That is the simplest explanation. Yeah, I'm describing 4 common, more popular learning methods to generate new molecules here. And these are very, very successful nowadays. So what was promised in the 1980s is now becoming possible in in this decade. But still, the question of synthesis, can you synthesize those molecules that generated by machines? That is still a challenge. And people are applying, again, some kind of reinforcement methods, to incorporate synthetic feasibility also into the generative approaches. In this case, you are including that as a part of the generation process. Here you're generating molecules, optimizing it, and then checking the synthesizability score. So these are still challenges, and people are working towards it. It is not a solved problem, and any advance will be very, very helpful here. So I just have to give you a little introduction to what is the synthesizability, right? When chemists look at a molecule, they have a process called retrosynthetic analysis. They go back, what are the smallest units here which are commercially available, and I put together. So you go take a molecule, break it down to small units, and then build it back. That's how that particular formalism was developed by E.J. Corey. What happens in synthetic mind was formalized by Professor E.J. Corey in 1960s. And later on, he actually, with computational people, he actually developed a method called LASA, logic and heuristics applied to synthetic analysis. This is a very popular thing, but it's based on, it's a knowledge-based approach, and other expert systems also people have developed. And people also developed something called synthesizability score that I will come to that later. And so we wanted to evaluate what are these methods available currently, which is assessing synthesizability of a molecule. And we looked at 5 of these: Cynthia, SciFinder-N, ICTOS, Reaxys, and ChemPass. And we tested it on one of the breed generated molecule. Remember in 2004, we published a paper where we can hybridize molecules. We took these 4 molecules in this publication and generated several molecules, like 9 molecules on the HIV protease. This HIV protease structure is where the molecule binds. So, but these molecules at that time, we didn't have in 2004 a technology method to evaluate its synthesizability. So I said, let me check if these molecules can be synthesizable or not. So I'll not go into details, but I'll give you a summary of this approach. So first thing is a computer-aided drug design enabled by AI methods. Then is opening up possibilities to explore much larger chemical space. By doing that, when you can get quality molecules, you're not working only in new or known space. You're going to novel space. That is the opening. And the AI methods are now generating drug-like molecules with optimal predicted affinities and also properties. But synthesizability remains a challenge. And as these develop, we can speed up drug discovery. And we are hoping that in very near future, these 2 methods of generative molecule generation and also synthesizability assessment, they become part of the toolkit for synthetic medicinal chemistry. The other part I want to talk, it's much more developed approach, so application of ML methods in property predictions, what we call ADME prediction. It is absorption, distribution, metabolism, and excretion. These are important parameters when we develop drugs. But this case, I'm focusing on specifically on the brain penetration. At Biogen, we are targeting CNS diseases like neurodegeneration, neuroinflammation, like Alzheimer's disease, ALS, Parkinson's disease, and multiple sclerosis. So these are all So any drug you want to develop to treat these diseases have to enter the brain. So brain is highly protected, and there is a specific, it's called tight junctions, so that nothing goes into the brain, so that it'll cause harm to the brain, right? So it's very, not only your skull is a hard skull, it's protected, but also when the blood is going through the brain vessels, it doesn't want to allow anything to, except for nutrients. It doesn't want to allow anything to get into the brain unnecessarily. And even if something goes in, it is pumped out by these efflux pumps, which are on the surface. There's one of the top pumps is called P-gp, and this is the structure of the P-gp pumps. So anything which goes in, if it goes in, even it'll be trapped here and it'll be ejected. So that's why it's called efflux pump. It's pumped out. So the brain is protected. Because of that, any drug molecules we make and we want them to enter the brain, these pumps take them out. So it becomes less effective. So we have to manage this challenge, that we want that molecule we design not to be a substrate for this efflux pump. So how do we do that? I mean, there is a crystal structure, but this pocket is very, very wide, very promiscuous. You cannot use structure-based drug design to do this. So we go by ligand-based drug design. So we wanted to use machine learning. So basically, if draw the molecule, you should have some kind of black box prediction method and says it is not good. It will allow in, not take it out, right? So you can train on molecules which are pumped out by this P-gp pump, or which are let stay in. So if those two classes of molecules, if you have, then you can design, you can use the learning methods to train these models. That's what we have developed here. We have about 2,300 in-house compounds, and if the efflux ratio is greater than 3, then we call it yes, and if it is less than 3, it is no, and you can train that model, and we do this feature engineering and all that, and then we use these algorithms, single machine learning methods and ensemble machine learning methods to train the models. And once you train the models, any new compound you synthesize, you put it into this model and predict. That helps us speed up drug discovery for CNS. Okay, so this is the results. I will not go into the details. I will say this 0.5, 0.58, 0.53. These are all pretty good prediction. Kappa CVs are 0.5 or above. Is a good successful prediction methods. I see that support vector machines algorithm performs best in this case. And for any good model, you need good data. Not only good quality data, but also it has to be representative, right? So if I'm want to scan larger space, I should have samples from all areas of that space in my model to build my to have, so that applicability domain is covering all the chemical space. As I show here, unfortunately, if you have these white circles is our chemical space. Actually, CNS drugs is a chemical space. We have orange data. This is the in vitro data for assessing CNS penetration. We have only limited all those things, and then CNS drugs are gray, and with the animal data is black. So it's not fully represented, right? So what we have done is that we took our total chemical space. We know where the representation is there. Where is no representation, we are actually sampling that space so that we have full data. So generating data is very important. So so just to conclude by saying that machine learning methods are very, very successful in designing CNS penetrant compounds, and SVM has performed best, but we can improve prediction on novel space by having more data. So finally, I want to say that we have adopted a lot of novel technologies in drug discovery, but cost of developing drug, discovering drug have been going up, and the time it takes has been also going, longer. Instead of improving, new technologies are actually making us do more work and slowing us down. Is AI going to be different? For the last 3 decades, great innovations have been, adapted to influence drug discovery, but cost and time has been going up, right? So is AI different? So current indication is that at least now there's a little bit of flattening of line. Maybe it'll improve. So that's a big question. We'll be monitoring. So I will stop here, and I want to thank my colleagues at Computational Chemistry Group at Biogen, who are listed here, and my leadership team, Chris Hilal and Annabella Ila Lobos for their support. Thank you very much for your attention, and I will take any questions you may have. Thank you.